Welcome back, physics fans, and here we are with our fifth lesson in the chapter of constant velocity. Okay, and here we're our fifth lesson, position versus time graphs. So jot this down. It's not handed out notes this time. You have to copy them down. An object at rest located 3 meters from the origin. So we're trying to do a position time graph here. An object at rest positioned and located from the origin of 3 meters. What does that look like? Okay, so you're at 3 meters. What we measure is in the y direction if you're math, right? Or in the range, up and down. And as the time progresses along, 1, 2, 3, 4, 5, and that's this time measured in seconds, which is our x direction, our location doesn't change because you're at rest. So you're still at 3, at 2 seconds in, you're still at 3, at 3 seconds in, you're still at 3, and it continues on. You're at rest, you're not moving. So we'll connect those up. And we get nice straight line. I'll put an arrow on there. Okay, not only is this straight, but it is also what we call flat because it has a slope of 0. If we had a line that's straight like this, that would not be flat. That would be angled, but it would be straight still. Okay, jot that down. On this graph, I would like you to graph the position of an object that is leaving the origin at 1 meters per second. Leaving the origin at 1 meters per second. Yes. Origin is 0, correct, thank you. So origin is 0, 0. That's the position definition we measure from the origin. So we're starting at 0 and leaving at 1 meter per second. Well, first of all, that's a velocity, or yeah, it has a good direction. It's positive. So it is 1 meter every second. 1 meter per second. So after 1 second, they will have traveled 1 meter. So put that dot in. After 2 seconds, would have traveled another meter, so it would be up to 2. And at 3 seconds, it'd be 3. And at 4 seconds, and it just continues on. And at 5 seconds, goes up another meter, goes another meter away. We now draw our straight line. It certainly looks like a straight line connecting those. Let me just get this not so jumpy right now. Well, it gets pretty close. I'll draw an arrowhead on it. And just so that you see the points a bit better, I'll put little circles around them. And there is a graph of the position of an object leaving the origin at 1 meter per second. Draw that out, please. Okay, now we have our third example to do. Graph the position of an object sitting at rest for 2 seconds at the location of positive 4 meters from the origin, then moving at negative 2 meters per second back to the origin and stopping there. Okay, so I'll give you a few seconds to copy that down, and then I will do it with you and try to solve this together. So, graph the position of an object sitting at rest for 2 seconds at the location of 4. So it starts at 4, and it sits there for 2 seconds. So it's still at 4 after 1 second, and then it's still at 4 after another second. So that's where it sits after 2 seconds. and then it starts moving at -2 meters per second back to the origin. So it has to be negative because we're moving back to the origin and we're not moving away from the origin, and we're already in positive land. So, and what does a velocity of -2 mean? It's -2 meters every second. So that means it goes down 2 meters, -2, back to the origin because we're at 4, so it's back every second. So after 1 second, it goes down 2. It goes to here, it goes down 2. And then another second, it goes down to 2, and we're back at the origin. That is back to the origin. Anywhere on that baseline there is the origin. It is a 0 position. And then it stops there. So at time of 5 seconds, it's still there. Okay, let's just draw the lines to connect this. Almost. There, close, pretty close. And I'll draw circles around these points because those points exist. So that's what the position time graph looks like of an object that is sitting at rest for 2 seconds at the location of +4 from the origin, then starts moving exactly at -2 meters per second back to the origin and stopping there. Okay, and then it continues on, sitting at the origin. Notice how steep this line is? Not that steep, but it's steep enough. Compare it to this one, which is not so steep. The other one went down 2, went from 4 to there. So that's that steep one I was just saying for, right? Which one is a little bit more dangerous to ski down if you had to ski on here? So you have a skier here. There's his knees bent and his head and his arms. And there's the skis. That'd be like quite a hill to ski down. It's quite steep. So the slope of that is a lot larger. Okay, just looking at the slopes, helping you out. And now here is another one to think about. Which object, A or B, is traveling faster, and how do you know? I'll give you a second to jot it down. Okay, which object is traveling faster? A. Good answer. A is traveling faster. But the big question is, how do you know? Jonathan? Okay, good. You started talking math terms here. That's good. It's good. So if we take a look at A, and let's start drawing in that, there's the slope in math is defined as the rise over the run. And if we take a look at the same run for the B, this is the rise of A, and this is the rise of B. They have the same runs, so the fraction will be much bigger in A. So how do you know? The slope of A is greater. Okay? Does anyone need more time for that? No? Okay. Let's describe these three motions. So now we have to write down some words or describe them. So I'll give you a few seconds to try it out and do a description for each one of them. How about that? A is at rest at the position of positive 3 meters. Okay, with that type of description, let's take a look and see if we can get down B. How about B? Starting at position of positive 3 and has a velocity of plus 1 meters per second. How do I know that? First of all, because it goes over in 2 seconds, it goes up 2. So the rise, now just take a look at this. This might be an aha moment. The rise over the run is, and it goes up 2 meters. So that's the rise. And the run goes over 2 seconds. So the 2 over 2 is just 1. And the units are meters per second. See that? The units are meters per second. What quantity that have we learned is units in meters per second? Velocity. So it turns out that the slope of a line on a position time graph is the velocity. So that's how I dared to write down with a positive velocity of 1 meter per second. With that knowledge, try to get C in a little bit more detail than you might have already written it down. Try out C. Okay. Okay, let's take a look. I wrote down C starting at the position of positive 3 meters. Get rid of that space in there for now. And let's get rid of the capital W, being picky, with a velocity of negative 0.5 meters per second. Why negative 0.5? Well, negative and 0.5 are things that I have to explain here. Let's do it in, I guess I'll do it in blue. This goes down 2. This is a difference of negative 2. It goes down 2. And that unit is meters. So that's its rise. And the run is 1, 2, 3, 4. It goes over 4 seconds. So the slope of that line is the rise over the run by definition. And the rise is negative 2 meters over a run of 4 seconds. And when we divide that, we get negative 0.5, and the unit is meters per second. And that is a velocity. So the velocity of 0.5 meters per second. Okay. So we're coming up with a rule here. And it's our graphing rule. Graphing rule number 1. The slope of a position time graph, put a dash there, time graph, is the velocity. The slope of a position time graph is the velocity. And we're going to play a little bit, and then we'll come back to the graphing rule number 2, but I'll have a space for it already. Graphing rule number 2. But we won't have that for another 10-15 minutes. Okay. So the app I'm showing you right now, if you just Google, if you want to play with it online yourself, you would just go type in PhET, which is physical experiments, physics experiments, and type in moving man. That's lots of good learning there, but we'll just do the moving man one today. And when you get it running, it looks like this. Now this one has buttons up at the top, and we just want to click on charts right away, just so we start seeing the graphs. And we're not going to look at the acceleration right now. That's the next chapter. So I'm just going to get rid of it by hitting the minus sign there, so we only look at the velocity and the position. Okay, this is 20 seconds. I don't need that much time. I only need 10 seconds. So I'm just going to reduce this down to 10 seconds. And now let's just take a look at it. I can drag this guy around anywhere I want and put him anywhere. I can leave him at the tree. If I want him exactly at the tree, that's -8, and type that in. And I can put in a particular velocity, but I'm not going to right now. I'm just going to, let's put him at -5 and a velocity of 0. Let's see what the graph looks like. He's not going to move. He's going to be at rest. What does it look like when it's graphed? Okay, so there's 5 seconds of him sitting at rest. The position is -5. We've done that. The velocity is 0 all the way along. No difference. I'm going to zoom into the velocity. I'm never going to go 12, although some people will want that, of course. Let's put a velocity of 2 right now and play it. Okay, so he's changing position, and the velocity goes from 0 to 2. Okay, the typical 8-year-old boy at this. Let's get rid of the acceleration, and let's put in a velocity of 200. There we go. Bam, right into the wall. Okay, let's reduce this down so you can enjoy that online too. There we go. Or we can pause it. He's sitting over there, and he's hitting the wall right away. He just went right up there to the wall and is sitting at 10. Let's go -50 and play it from there. Bam. He just runs into the other wall. He just goes from wall to wall. Okay, and -50, that's -12, so it's way down there, no good. Okay, let's just do some more common ones. Let's reset it. Yes. Get rid of this. Start them off at -8. And let's do a velocity of 2 and see what it looks like. See if you can kind of visualize what it's going to look like first. And here we play. I'm going to stop him or try to when he's at the house. Oh, just a little bit further. I'm now going to set the velocity to 0. Let him wait there for a bit. 2 seconds. No, that was 4. And now I'm going to do a velocity of, how about -4? Okay, these are the 2 graphs that they gave me. I'm just going to zoom in a little bit here because this one, I don't get any weird, I don't get nice numbers. If I go back, I guess that's as good as we get if we get nice numbers. I'll zoom in. I'll just take it as what they give me. There we go. So I'm just going to grab that over to my notepad, and we'll take a look at what's going on here. Initially, this starts off at -8, and it goes all the way over to +8. So the rise of this from -8 to +8, that's a +16 rise. And the run of this is 8 seconds. So the slope is the rise over the run, which is +16 over 8, which is equal to 2 meters per second. These are in meters, these are in seconds, so it's just 2 meters per second. And that's the number that I did punch in, and that's what's represented here as a 2 in the velocity, and the velocity didn't change. Changing velocity would look like this. It's not that. It's flat, so it's not changing, and it's 2 all the way to that point. Okay? Here, it goes right down to 0, which represents a staying at rest at +8. And here was a velocity of -4. And that went for 4 seconds. And the rise over run, here we go. This went down 16. It went down 16, and the run was 4 seconds. So the slope is -16 over 4, which is -4 meters per second. Whoops. -4 meters per second. I don't know what's going on there. That's my bad handwriting. Okay, and that was the velocity that we typed in, -4, and it stayed -4 all the way along. Because it stayed -4 all the way along, the slope didn't change, so that is a straight line. Now, here's an observation. What is the area of this? Okay, we have a rectangle there, and the area of that rectangle, or of the box, but that's a rectangle, so we'll do that. That has, I'll just say box right now, is equal to the base times the height. That's the area of a box. The height of that is 2 meters per second, because that's a velocity. And the base of that is 8 seconds. So 8 seconds is the base, and the height of that is 2 meters per second. And we multiply it, just take a look at the units cancel. Seconds up top, seconds down below cancel, and we get an answer of 8 times 2, which is 16, and the units is meters. What is 16 meters? During that 8 seconds, 16 meters is how much it rises here. And how much it rises there is its change in position. Let's see if that holds true over here. We'll do this green box over here. Okay, the base of this is 4 seconds, and the height of this, okay, is actually negative, and the height is -4 meters per second. That's that height of that box, because that's the speed that we had it at, is -4. So the area of this, whoops, sorry, area is base times the height, and the base is 4 seconds, and the height is -4 meters per second. So when I do this, I get -16 meters. And what is that? During that time frame, that's how much it moved. And it so happens that here's rule number 2. The area under a velocity time graph is the change in position. And that symbol is delta P. What do I mean by change in position? Well, let me just explain that. Why doesn't it give us the position, but it just gives us the change in position? Let's go back to this. Let's hide. There we go. So let's play this back. There's the velocities. It sits there for 2 seconds, or 4 seconds, sorry, and then goes back. So I want to know, by looking at the red graph, where is it at 0? Where is it at 0 meters? You can find it through some logic and some calculations, but there's no clear point here that says that where it is at 0. If I show you the position graph, you'd go, oh, at 0, it's right there, because that's where it crosses, and right here, that's where it crosses. So it's at 0 here and there, because that's what it is. But if I just show you the velocity time graph, you don't know where I started, so you would not know where I am. In fact, I could get that same velocity time graph, but start somewhere else. And therefore, you would never know by looking at the red graph where I was. You would not be able to tell that I was passing it at 14 and passing it at 4, the origin here. Okay? Let's just show you. Okay. Let's take a look at this. Look at this velocity graph. Can you tell me where he is passing the origin? It sure looks like he's at the origin here, right? Because that's 0. But that's not the origin. That means he's just stopped. That just means he's just stopped there. This just means he's traveling like at 2, and then he's traveling at -4 or -3 maybe. Then he stopped. Then it looks like he's traveling at 1. But this graph, by looking at just the graph, you can't tell where he is. But if I pull up just the position graph, can you tell me where I crossed the origin? Well, it looks like I started at the origin. And at about 3 seconds, or a little after 3, I crossed the origin. And then I crossed the origin down here at 18. So if I play it back, here we go. There's the origin. And then he stopped way back there for a while. Anyways, so we're getting a little bit of understanding of what's going on by looking at the graph. And what does this velocity graph tell us? It can tell us how much he moved during this time frame. If I calculate the area there, that little area that I'm squiggling out and I'm not, that area is equal to this height, which is about 4. Then if I calculate this area, and let me just copy that. Let's just do that just quickly, and we'll end up with this as our final part of the lesson. If this area, which is base times height, and that's 2 and 2, that's 4. That means that position there is 4 because I started at 0. Okay? If I didn't start at 0, I could have started here and went up 4. Okay? We just know that you changed 4. We didn't know where we started. Given where we started, yes, we could calculate it. And then this area here, we have to go right to the 0 line. This area here is the base, which goes from there, which is just after 2, to there, which is 5.5. I would call that maybe 3.5 seconds. I'm just guessing quickly now, just to get through the lesson. And this is roughly, what is that? 4 maybe, -4. So 4, -4, -4 times that will be 14. So this area, is equal to base times height, and the base is 3.5, and the height is 4, so this is going to be -14. If I start from 4 and I go down -14, I get pretty close to 10. See that? The change is there. So I could predict drawing this blue line because of this, and we'll come up with that another day. Then he's at rest to there, and then I can calculate this area, and if I calculated that area, I could find out how much it moved up. Okay, I'm not going to go anymore. That's enough. Thank you for paying attention. Hope you enjoyed some graphing fun. Okay, graphing pain. Talk to you later.